Okay, we're going to get started here. We're still doing the unknown B from yesterday. I just turned on the hot water bath again. I'm going to take a look at this. Regarding the quizzes, make sure you turn those in, because once I grade that series, then quizzes after that are going to be considered late. And so I'll be doing the nomenclature shortly. But, some messages out to some people, but make sure you check those messages, Canvas.
Professor?
Yes.
Is the final exam going to be take home?
Final exams take home, yes.
Oh, okay. All right. Thank you.
Okay, the hot water bath has gone down the level. So I'm going to put some more water in here. We never want to let hot water baths go to dryness. That causes trouble there. All right, as I let that one go, we'll do something else. In the meantime, I'm going to prepare one more sample here. Were there any questions? No? Okay, we're going to take a look at this sample here. I'm going to do the first step. I'm going to precipitation. We're going to analyze for the cations. We're going to skip the anion analysis on this one here. And so I'll just add excess. We had a white precipitate with HCl straight off. And so I'm going to heat this one up as well. Here. We'll have that sample running. Okay, so I have this. I'm going to filter this one out. See what we get. Test. I think I accidentally spilled some water in that one. Grab my funnel. I'm going to analyze this further, so I'm actually going to wash the funnel with some soap, water. Okay, and then since this is pretty full, I'm going to get a small well, since we're running out of glassware, I'm going to use Erlenmeyer to filter it in here. So let me wet the filter paper. Yeah. Dump out the excess. And then let's go ahead and filter this one. So it looks like a lot of the white PPT did not dissolve here. Set this aside. In this case, I'm going to rinse a little bit of the remaining residual precipitate in the test tube. I'm going to use this as a rinse. So I'm going to try to transfer more of the precipitate over by rinsing this. And I'm going to reuse this test tube probably here for the subsequent analysis. So. Or maybe not. Let's see. Okay. So the first thing with this is we're going to test the precipitate. So I'm going to wash the precipitate with some water. And yeah, one more time. Okay, while that is draining, we'll check the filtrate here. And so the filtrate I'm going to test with potassium iodide in the next step to see if there's lead. And so let me get my Ki solution. Okay, so here goes. All right. Okay, when you take a look at that, there's quite a bit of yellow-orange precipitate that's just formed. And it gives a cloudy suspension like that. I got to make sure I get all the lead precipitated that I can, so I'm going to add some more. Then let this sit I need to let this settle a little bit in order to determine if there's going to be more precipitate that forms here. And so I definitely got a yellow PBI2 precipitate, but I don't want lead to get mixed up with the filtrate. So I got to make sure I get it all out. The separation is important there. Okay, come back and retest that. Now, to the original white precipitate here, okay, I have my washed precipitate, and then I'm going to test this with some sodium hydroxide, 6 molar sodium hydroxide, to see if it turns black. So let's go ahead and give this a shot here. Actually, I'm running low on sodium hydroxide, so I'm just going to pour it in this. So that's the sodium hydroxide there. But I don't see the same distinct color change that was observed here. If you take a look at this, here, let me grab this. This was our positive test in the previous one. And this is this test here. There is some slight discoloration, so it could indicate some trace amounts, but it looks like I don't have much, if any. And so this is probably undissolved lead. You know, the lead was supposed to dissolve, but as I said before, the lead can go over and mix with the silver chloride precipitate, causing a false positive for silver chloride. If this were silver chloride, it should have turned black like this. So it's probably just some residual lead in that I wasn't able to completely dissolve all the lead. And that's probably what we got there. And we definitely have a lot of lead here. So that's what we got so far. All right, now the lead, I just got to make sure it was completely precipitated. So to make sure it was completely precipitated, it's hard to see, you know, if any more precipitates. We can try adding another drop of Ki. Let me do that and see if it becomes more cloudy. So we have to look at it very carefully. So I'm going to just drip it down the side, but still it's going to be hard to see if it becomes more cloudy. It's looking like it's not really becoming more cloudy, so I probably added enough Ki. We'll test it afterwards. And so what I need to do is I need to separate this from the solution. And so I need to filter this again. So let me get rid of this filter paper here. Although there could be some small amounts. So there is some discoloration to this. But if we have silver, which we should have at the same level, then it's probably just something else. Probably just the lead. So I'm going to rinse this. We need to analyze the filtrate again. So I'm just going to rinse this off. Rinse it with some DI. And then set this up to filter out the Ki. With the funnel. Just wet the paper. dump off the excess. All right, so what am I going to pour this one into? The volume's starting to get high. And so pour this into a small Erlenmeyer. Now, the precipitate is the last step for the lead. And so I'm going to test this solution here for barium and manganese to see if we have any. So let me take a look at what the next step there is. So the next step would be to precipitate out any barium ions that are present. So let me set this down here, and then I'm going to get some sodium bisulfate to see if there's any barium ions present. All right, this is still going. It's a little bit slow. And so as this is filtering, I'm just going to go ahead and add this to save a little bit of time, just to see if we get any precipitate in the filtrate. All right, that was 1 squirt of barium sulfate, sodium bisulfate. And so I put in 2 squirts of sodium bisulfate, but there's really no precipitate that's forming here. And so it doesn't look like there's any barium ions, which should have precipitated out. Okay, so if there's no barium sulfate precipitate, then we go on and look for manganese. We're going to look for manganese by adding sodium hydroxide. And so I need to get some sodium hydroxide here. Grab that. So my little dropper bottle ran out, so I went to grab some more sodium hydroxide. You can see that some people spilled some sodium hydroxide on this, and as it dried, we get solid sodium hydroxide here. And so there's spills on this side and spills on this side. Normally when we grab a bottle, we grab it by the label, but there are 2 labels here. And so this had drippings on both sides. And if you touch that, that's just solid sodium hydroxide we're touching. And so fortunately I have gloves on. And then I'll just grab it from this side here. And I'm gonna just refill the bottle, the dropper bottle here from the stock solution. Sometimes you have to do this yourself in lab. So there'll be large bottles of stock solution. And again, when you pour, you want to grab it by the label, or you want to look, what side is the drippings on, and always pour it so that the drippings end up on the same side. That way, That way there's less risk of the contact. You can see all the sodium hydroxide on my gloves here. That's solid sodium hydroxide. So what I'm going to do is I'm just going to wash off my gloves so I don't get that. You definitely don't want sodium hydroxide, especially solid sodium, pure sodium hydroxide in your eyes. Sodium hydroxide you can buy as solid. It would be just drain cleaner, basically. And so you definitely don't want a drain cleaner in your eyes. It's going to cause some severe damage. Well, anyway, we got some nice precipitate of the lead-2 iodide. This is what the lead-2 iodide looks like here. It's a nice yellow precipitate. Okay, we're unsuccessful at precipitating out any barium, so there's no precipitate here with the bisulfate. And so what we're going to do is we're going to try to add some sodium hydroxide here and see if there's any manganese. All right, this dropper is not so great, so let me get a dropper. Okay. So that's 1 squirt of sodium hydroxide, and there's no precipitate there. We'll just put 1 extra just to make sure. That's 2 squirts of sodium hydroxide, so there was none. And so this one also consists of just 1 cation. And the cation was, let's take a look at the precipitate here. Yeah, it's not really, it didn't really turn black, brown. There is some discoloration to it, but it could just be discoloration. And so it looks like this unknown only contained lead ions, and it was nitrate, lead and nitrate ions. So that was that. All right, so this is going to go in the waste. That had some lead in there. Okay, how about this one? Let's take a look. Hopefully this one has some more. So this one's been cooking for a while, and we still have some white precipitate in there. Let's see if that precipitate dissolves. Precipitate should dissolve if it's lead. But then again, lead chloride is insoluble. And so insoluble means that, it depends on how much water and how much heat we have. And so it is possible that not all the lead chloride dissolves like in the last unknown that we had. We just don't have enough water to dissolve it all. And so this white solid that's left in here could be excess lead-2 chloride that just won't dissolve because I need to add a bunch more water, or it could be silver chloride. So what we're going to do is we're going to filter this out and then test this white precipitate to see if this white precipitate turns black, then it's silver chloride. If this white precipitate doesn't really react with the sodium hydroxide, then it's probably just excess lead-2 chloride that wasn't completely separated in the previous step. And so this one I'm going to dump out here, and then I'm going to just rinse off the funnel. We're going to reuse it here. So dump that in the solid waste. And then I'm going to rinse this off into the waste since that was lead. And I'll give it a more thorough rinse off here. These tests aren't hypersensitive. If these were hypersensitive tests, I'd be very careful in washing, because I'd have to make sure that my washes are very thorough. Otherwise, contamination, cross-contamination could yield positive test results. But these require quite a bit of precipitate, and so they're a little bit more forgiving as far as small amounts of contamination might result. And so here, I'll just fold the filter paper into quarter. And then let's go ahead and rinse that off. Make sure that test tube's clean. I'm going to filter it into this test tube since the liquid volume, actually, liquid volume's kind of high. I need a large test tube, which I don't have right now. I'm going to do some more. Oh, actually, I do. I'll use this one. This is hot. If this is too hot, we're going to use the test tube clamp to hold this. Here. Let me just try to see if I could get this precipitate to dissolve or not to dissolve. Probably about it. So there is a little bit of precipitate left in there. Let's go ahead and filter this. End up using that one again. Okay, one thing you notice is it looks like the filter paper didn't catch much of the precipitate. You know, there's not that much precipitate in there. And when we look at this, it looks like the precipitate is down here, and it seems as if there's a hole in the filter paper, but there is no hole in the filter paper. What happens is the lead, you know, in boiling water, we had saturated. You know, I couldn't get any more lead to dissolve. It was saturated. And then as I filter, it cools back down because this test tube is not hot. This test tube was at room temperature. And so as that solution hits the cold test tube, then the solubility of the lead-2 chloride goes way down and it precipitates out, you know, becomes super saturated and precipitates out. And so this is just lead-2 chloride that just precipitated. If I put this back in the hot water bath, it should dissolve again. So I'm going to put it back in there. Now the question is that excess lead-2 chloride that just wouldn't dissolve, or is that silver? And so we're going to test this with some sodium hydroxide. So I've got my waste beaker over here. And I'm just going to pour some sodium hydroxide and let the filtrate go into waste here. And let's see what happens with this. So I get the sodium hydroxide, and we're going to test this. All right. Get a little bit more sodium hydroxide here. And a little bit more. All right, there was a little bit of discoloration, but pretty much that little tiny bit of precipitate dissolved. And if it were silver, it wouldn't have dissolved. In fact, I just have a couple of flecks left in there. I think if I put one more squirt of sodium hydroxide, I have no more precipitate. So what that tells me is this is not silver chloride. Silver chloride wouldn't have dissolved in sodium hydroxide, and would have turned into a black precipitate from a white precipitate. And this completely dissolved. So what that was lead-2 chloride that I just couldn't get to dissolve. I didn't have enough water to dissolve it all. So that was the situation. And so it was kind of very tricky because things don't always work. Like expect them to. And sometimes it's more difficult to interpret the results. So if we look at this, we had a lot of precipitate in there before, but now take a look at how much precipitate there is. So this is lead 2 chloride. You know, at room temperature, it's not very soluble or not as soluble, so it precipitates out. But if I just reheat it, you know, it just redissolves. And so, in fact, if I look at this, this pretty much negligible. Now, let's go ahead and heat it a little more. I'm going to watch my water bath. The level's getting quite low. And then refilling it. Okay, so back here, it all dissolved again. Okay, so it all dissolved again, so that tells me it's got to be lead, but we can confirm that it's lead by adding potassium iodide. And I should get a nice yellow precipitate once again, so let me go ahead and add the potassium iodide to this. So what I did was I redissolved. There's no more precipitate in there. I just redissolved it using hot heat, and then I'll just add some Ki to this, and as expected, we get a nice yellow precipitate. Now I got to make sure I get all that precipitate, I mean all the lead out of there, because I don't want lead to interfere with the subsequent analysis. And so this is good. Do you see the precipitates on the bottom? So I could see the colorless solution on the top. And so what I'm going to do is I'm going to watch the colorless solution as I drop the potassium iodide in there. If I get more cloudiness, that tells me I haven't completely precipitated it. In this case, more cloudiness developed, and therefore there's still lead. I need to get all the lead out of the solution and into the precipitate. So I'm going to just keep adding the iodide basically until I stop seeing precipitate being formed. So I'll add an excess. And right now it's cloudy throughout, and it's very hard to see if I'm getting additional precipitate. And so I'm going to add a little bit excess just to make sure. So that's a little excess there. And then what I'm going to do is I'm going to just put that back in here. I'm putting it back in here just to try to get it to coagulate. You know, that's one way. Or the other way I could try to do it is to cool it down. You know, cool it down and then see. Okay, if it's not settling down very well, I can go ahead and try to filter it. I try to filter it and then see if any more precipitates in a clear, colorless filtrate. And so I'll probably end up doing that. Probably end up just filtering it. I'm going to shut off the heat. The water bath is getting quite low. And then cool this down a little bit by running it under the tap. I'm cooling it down just to make sure, you know, I get as much of the lead out of solution as possible, because things are less soluble at cold temperature. In fact, sometimes we use an ice bath. In this case, it would be good to use an ice bath, but I don't have it right now. So I'm just going to go cool it down to room temperature, and then I'm going to go ahead and filter that to another Erlenmeyer here. Dump that filter paper. Okay, so I'm going to rinse it into waste. There's probably a lead that was residual lead that was there. And give it a more thorough rinse there. Yeah. Okay, and then get another piece of filter paper. Try this. wet the filter paper, drain off some excess, and then go ahead and filter. Okay, let's see if it's.
It hurts so bad.
It really hasn't settled
What'd she
enough.
say? She's like, oh yeah, there's a big lump there, but she fixed it.
Oh yeah, it's even. You still have a little bit here.
I know, but it's just swollen, she said.
Okay. She couldn't break this one?
So we'll go ahead and filter this into this. One thing that people do oftentimes is use the stir rod to direct the solution. So I'll just show you that here. So I had the filter set up here, and oops. Shoot. Another thing you got to worry about are fatigue test tubes. That is, people stir these, including me. I was stirring this, and as I was stirring it, it punched a hole into the bottom of the test tube. Do you guys see that? Probably not. It punched a hole into the bottom of the test tube. So unfortunately, my solution is now all over the counter. It's too bad. So I'm going to rinse this off into waste. My waste jug here. And then I'm going to toss this into broken glass waste. We have broken glass waste over there. It's in the blue and white box. The blue and white box are where all the sharps and broken glass go. And so let me toss this. And so if that happens and your unknown solution is all over the counter, obviously you can't do much about that. So I'm going to just toss this. Into the waste jug, and now I have to deal with cleaning up this. Now, fortunately, the lead, the lead was mostly as the insoluble PBI2. And so it's not very soluble PBI2. So that's a good thing. There shouldn't be much lead in solution. And so this liquid's probably, the lead is going to be the precipitate here. So you probably can see that here. There's some on the test tube rack here. So when we clean this up, I'm just going to make sure I have the gloves on, and then I'm going to try to wipe up the solid as much as possible. I put some paper towel on here to absorb as much of the spill as I can. Here. And so this precipitate is all PBI2 here. And if it were PB2 plus AQ, it would be a lot more hazardous than PBI2. Since the lead is locked in that PBI2 lattice. But still, you want to minimize contact. So fortunately, I have gloves on. Use the gloves. That happens. So in Chem 1B, what I normally have the students do, and this is something I didn't do, I was just using the test tubes, is I normally have the students anneal the test tubes. I'm going to throw this into solid waste. So this is paper towel that's contaminated with PBI2, and I have a solid waste beaker here. I'll just put that in the solid waste here. And then I'm going to clean this up with some soap. Soapy water, paper towel. Let's move this out of the way. So what happens is people, are repeatedly poking, trying to get that lead to dissolve, right? And so they're poking at the bottom. Here's a chunk of the test tube. I'm gonna put that. You got to watch out because as far as accidents go and as far as safety goes in the laboratory, burns are number one, and then cuts are number two. Broken glass, sharp edges. And then spills are number three. They spill stuff on their hands and arms. And so we've got to wash off. For spills, obviously we're going to wash for 15 minutes. If you spill anything on your arms, wash off for 15 minutes. You don't want anything in your eyes. Unfortunately, nobody's gotten anything in their eyes. Most people wear their safety goggles. But if you were to get something in your eyes, then also you want to wash for at least 15 minutes. Now, we had a spill on the counter. And so the lead was in the form of the PBI2 solid. And so that's pretty easy to get, to clean up. And then the other stuff was barium ions. Barium ions are also somewhat toxic. People use barium sulfate suspensions for imaging in like CAT scans, because barium is an excellent X-ray absorber. And so barium is fairly toxic, but people drink barium sulfate. And the reason they can drink barium sulfate is because barium sulfate is highly insoluble. And since the barium's locked up in the sulfate lattice and it doesn't really dissolve in stomach acid, it's not going to lead to toxicity. Now, if you did the same thing with barium chloride, you'd be in trouble because the barium is in aqueous phase and then barium can attack, and disrupt your normal biological functions that are going on. Let me talk this. Fortunately for me, I had gotten the lead, out of solution, at least from what I can tell, practically all of it or all of it. And so then I can clean this up. Okay, not too much trouble. You don't know how well people clean the counters up. So normally what I did when I was taking lab, I would always clean the counters before I started an experiment in case, the previous person using the lab bench spilled something but didn't really clean it. That often happens. So it's good lab practice just to clean the counter before. And that way, if you spill something, you could still possibly recover it. Unfortunately, what we spilled was a solution, so it would have been very difficult to recover that. All right, what time is it? 12:17. So it's enough time for to run one more. And so I'll make up one more unknown. But before I do that, this is what I have the students do in Chem 1B. I should have done that before I started. What happens is this. What happens is people are trying to dissolve the crystals or trying to stir the mixture, and they keep tapping the bottom of this. As they keep tapping the bottom of this, it causes stress, because you're tapping it and you're pushing the bonds. And the bonds like to be at certain angles. For example, tetrahedral angle is 109.5, but if you're tapping it, and so it either goes wider on one end and then it goes narrower on the other end. Well, that places a tremendous amount of stress on that bond and it weakens that bond. And so the bonds end up getting weak. And so this is made out of glass, and glass is made up of a whole bunch of silicon and oxygen tetrahedron plus other stuff in there. And so that tetrahedral bond angle gets all screwed up by tapping this, and it causes stress in the structure. And eventually, one day, somebody will barely tap it. Like they'll tap it. I didn't even tap it. I wasn't even tapping it. I was just trying to move it to and filter it. But the stir rod was sitting in there, and it was just the weight of the stir rod punched a hole in there. And so one day somebody's going to barely tap it, and boom, they punch a hole in the bottom, and all their unknown spills out. It's happened so many times in Chem 1B that I started having the students do this at the beginning of the semester. Out of matches. Um, Normally one can get matches at the stockroom window, but they put them away somewhere. You want to look through all the drawers. So I took this box out of the drawer I use for check-in. Okay, so let me show you what I have them do. I need to turn off the light. Make it easier to see. So we have the flame here, and the test tube. Need some test tube clamp. Test tube clamp here. And so what you do is you don't want to heat it on the hard part of the flame. The hard part of the flame is right at the tip of the cone. You could, glass takes a lot of temperature to soften, but you could heat it here. Actually, take a look at the color of the flame. Do you see the color of the flame? You know what that color is from? The yellow flame. The yellow flame is not because of a lack of oxygen. This yellow flame is because of sodium ions. If you sprinkle salt in a flame, you'll get this yellow flame, and that yellow flame is due to sodium atoms being excited. It gives off yellow light. And so this is not producing soot. It's not producing carbon monoxide. It's just yellow because of that. And so what we'll do is you could heat it on the hard part, but what you want to do is you want to heat it on the soft part, above the cone here. And then you heat it for a little bit to soften, and then you remove it from the flame. It's actually glowing, but in this case, what we'll do is we'll just let this gently cool down. And so what that does is when you warm it up, there's a lot more mobility. And so the bonds can go back to the original, so the bond's supposed to be at 109 degrees, and it got distorted. Now the bonds can relax back to 109. And essentially, we're letting the bonds relax to 109, and then we're gradually cooling it down. We aren't quenching. If I quench this in water and rapidly cool it, then it's not going to get the optimum lowest energy bond angle. So what I have the students do is I just have them do a quick anneal. Anneal all the bottoms of the test tubes so that we don't punch holes into them. Okay, when you have hot glassware like this, you always point it away from you. That way, you know, you always grab the end that's closest to you. So if I were to grab this test tube, I'd grab it by this end. But if you have it pointed towards you, you'll grab the hot end. And hot glass looks the same as cold glass. And this is how people end up getting burned. And so what we end up doing is we end up letting these cool down on a ceramic plate, pointing the hot end away from you. So don't set it on this counter because you can see people have set hot objects on this counter and it's caused some damage there. And be careful of setting it like this because usually if you grab the end that's closest to you, it's going to be the hot end. And hot glass takes a long time to cool down. You know, it's not as rapid. Metals are a bit quicker, but still metals take some time to cool down. This is still radiating a lot of heat here. So if I were to grab this with my fingers, I'd get a burn for sure because I can feel the heat if I hold my hand above this without touching it. All right, so unfortunately that unknown didn't work. That was failure, so we lost it. And so I'm going to make up another unknown here. And we'll just analyze it and see what happens. Singular unknown. Okay, so I have this unknown, this is another CCS, and let's see what we can do with this one here. And so the first step is to add my HCl. Just get some HCl here. And see if I get a precipitate. Okay, this particular unknown, I just put in a squirt, which is, in this case, a squirt's less than a mil. I'll put another squirt in there. For sure, this one is resulting in no precipitate. So if I get no precipitate here, it's telling me silver is not present. And it's also likely that lead is not present because lead, we need, remember, we need the hot water to dissolve the lead. And this is just room temperature. And so I'm testing negative. And so this unknown is negative for lead and silver. So just to make absolutely sure about the lead, you know, maybe the lead is at low concentration, but just to make absolutely sure about the lead, I'm going to add just a little bit of potassium iodide to see if I get a yellow PPT, because that yellow PPT was very distinctive. And so I definitely don't have silver, but just adding a little bit of Ki to see if any yellow precipitate results, and there's nothing. There's no yellow PPT, there's no nothing. And I added, you know, like a half a milliliter to a milliliter of Ki. I got nothing there. And so, so no silver, no lead. That means we're going to go on to barium and manganese next. And so let's check if barium's present. Okay, with barium, I need to add the bisulfate. And so go ahead and do that here. See if I get a white precipitate of barium sulfate with the addition of bisulfate. So, okay, add that in here. Actually, nothing. I got no bisulfate precipitate, and so no sulfate. Okay, now the volume is getting high. If the volume gets too high, we can evaporate it. You know, decrease the volume sometimes. But let's see if there's manganese. And so I'm going to add my sodium hydroxide and see if I get a light brown precipitate with sodium hydroxide. Okay, I'm getting a precipitate here, but it doesn't look so light brown. Kind of looks white. But color can be very deceptive. This dropper is leaking, so I'm going to just pour from the bottle. Oops. Get as much precipitate as I can. Actually, that's about as much as I can get because that's full. It's full. Well, it's a slightly discolored. You can see there's a slight brown to it. So maybe this is the light brown precipitate here that we have. Okay, so I'm just going to go with this amount of precipitate here. I could add another drop, but I think that's enough precipitate to work with for the next step. And so what is the next step here? Well, next step is I need to filter this, and I'm going to wash off the precipitate. And so let me get my filter paper ready here. Actually, I had it ready for the last one. Dump this into the solid waste. Turn off the gas. And then I'm going to rinse this off into the liquid waste. Actually, the liquid waste has a lot of precipitate in it now. Rinse off the stem. The stem of this funnel is quite dirty. And then let me give it a rinse over here. Some more DI. Okay, get some filter paper. Okay, this filtrate we're going to discard, so we don't need to save it. We're not analyzing it for anything. And so I'm going to just filter it directly into the waste. Oops. So wet the filter paper here, dump off the excess, and then get this precipitate here, and we'll filter it into the waste. I'm going to hold the stem above the waste. I don't want to put the stem filter into the waste. This one I need to put into the sink. Only thing is to have to hold this. This is filtering slow. It looks like this precipitate is kind of silky in texture, so it's clogging up the filter paper. And so let me set this on a ring. Clamp it to the ring stand. This ring is extremely hot. I can still feel the heat radiating off of it. All right, so I have to add some nitric acid and some sodium bismutate to this. And so the situation is here, if I add the nitric acid, what that's going to do is it's going to dissolve my precipitate because my precipitate is manganese hydroxide. And then I'm going to add some sodium bismutate to that. And so going to I'm going to rinse off my my precipitate here. Some DI water. Now, when we looked at the precipitate earlier, it looked quite white in color, but take a look at the precipitate now. You know, it's definitely a brown color. You know, and so the color is deceptive. It's a lot easier to determine the color if it's not a cloudy suspension. If you look in the middle there, it looks white still. You know. But when you look at the solid that's collecting on the filter paper, it's definitely brown. So this is telling me, yeah, I think this is manganese. In fact, I'm pretty sure this is manganese. But what we can do is we can do confirmatory tests for the manganese. And the confirmatory test is with the nitric acid, that's going to dissolve the manganese hydroxide to make manganese 2 ion. And then once we have the manganese 2 ion, then we're going in solution, we're going to oxidize it to form purple potassium permanganate. And so let me grab a beaker here, and we can do that in a beaker. I need to wash it. And so this beaker was pretty dirty. So I'm going to wash it with soap and the brush. See, I still have a lot of dishwashing to do. But I'll wash it with, I don't know if you can see that. I guess you can. And so I use soapy water. It's not so warm right now. Give it a thorough rinse with tap water. Then I'm going to give it a final rinse with DI water. I'm not going to dry it. And so I have a beaker that's wet with DI water. It's clean now. Okay, let's take a look at the filtering. It's pretty slow. If you look at the drip rate, that's pretty slow. And we still got liquid there. So this is telling me the filter paper is pretty clogged. This is going to take some time to filter. Since, you know what, we have enough precipitate there. That's enough precipitate. And so what I'm going to do is, as long as I have enough precipitate, I'm going to time this here, bring this over. I'm going to speed this up. So I'm just going to pour off the remaining suspension in here, like that. And I'm going to just test this precipitate here. And so the first thing is I'm going to wash off the precipitate here. Let's take a look at the drip rate. Drip rate's still very slow. I have a bunch of solution in there. Okay, extremely slow. So I'm going to pour off this, and then I'm going to test this precipitate here that I captured. Okay, the nitric acid, like I said, is going to dissolve. Or should dissolve this precipitate. It's just, this precipitate is manganese 2 hydroxide, so we just have a double replacement type reaction. Here's some 6 molar nitric. And you clean pipette. Let's go ahead and take some of this nitric here. Do you see some vapors coming out there? When you see vapors, you should do this in the hood. I'm going to scan the side of this. Actually, I'll probably just test it in here. A lot of it didn't dissolve. I'll test two. I'm going to test the solution there. You can see the color. Oops, you can't see the color. You can see the color of the solution is quite yellow. Okay, that's from the dissolved manganese 2. And then you can see there's still precipitate in here. There. I have the sodium bismutate. Sodium bismutate is a solid here.
Professor, it's break time.
Okay. Actually, this is just going to take a minute. Let me just finish this right here. I just need to add 1 scoop of sodium bismutate
Okay.
to both. Sodium bismutate is a powdered solid like this, so you don't want to create a dust cloud of this, and you don't want to breathe this in. Normally, I recommend that the students do this in the hood because, you know, to prevent anything. And so I'm going to dump this. Oops, I just spilled some. Into the solution here. And let's take a look. You see what happened to the color of the solution? It went from the orange kind of brown color to a purple color. Put this back in here. And we're going to take an extended break, so because I'm going to move back to a different location. And so we end up with this purple color here, and it's hard to see because I ended up with a suspension. And so what I'm going to do is I'm going to filter this. I'm going to use the same filter paper because it's just the manganese that we're trying to get anyway. Try to filter this here. Just 1 second. Let me set this aside. So what we're looking for is a purple liquid. If you look at the bottom of this beaker, you can see there's some purple liquid there. Now, there's also some orange excess sodium bismutate. This isn't as purple as it should be because that's probably, I have too much manganese in there. So what I'm going to do is I'm going to, I'll just set this in the waste. I'm going to pour this in here since I have some extra unreacted sodium bismutate. And I'm just going to mix it here. Okay, now you can see it more clearly. That purple or that grape juice solution is permanganate. And so it's the red purple solution, permanganate. And so we tested positive. So this unknown had manganese. Unfortunately, all our unknowns only had 1 cation, so it didn't make it as interesting. I wanted more cations, but we're out of time. And so if there were more cations, then we'd have some more steps to it. Okay, so what I'm going to do is I'm going to stop here. We're going to take say a 20-minute break. As I'm going to change locations here since we're done with lab for today. I'll change locations and then we'll resume after that. And so I got to shut my computer off. I'm not sure if the room is going to close or not. If the room closes, then just rejoin it. But I'll stop the recording